every vertex of the set X is connected to the every vertex of the set Y by an edge. If the number of edges and number of vertices are same, then the graph is said to be an isomorphic graph. That's all. So dividing the graph into two, vertex X and Y is called the bipartite. Hello dear students, welcome to this session of Discrete Mathematics class. I am Mr. Niranjan, Faculty, Department of Computer Science, Vidhyaashram College, the Temple of Excellence. Now today in this session I am going to discuss regarding very important concept, that is regarding bipartite graph, isomorphism and the problems based on isomorphism. Now let us come to the first concept, the bipartite graph. Bipartite, bi means two, just partile, dividing. So dividing the graph into two, vertex X and Y is called the bipartite. Divide, bi means two, that is partile, partition. Dividing a graph, that is a bipartite graph is a simple graph in which the vertices of the graph are divided into two sets, that is X and Y. So dividing a simple graph, that is the vertices of the simple graph into two sets X and Y, such that every vertex of the set X, every vertex of the set X is connected to the vertex of the set Y. Every vertex of the set X is connected to the, every vertex of the set X is connected to the vertex of Y by an edge, There will be no edge between the vertices of the same set. There will not be same edge between the two vertices, same vertices. Such a graph is called as a bipartite graph, that is called the partition. So here a bipartite graph is nothing but dividing a simple graph into two sets containing the vertices X and Y. So two sets X and Y such that every vertex of the set X is connected to the every vertex of the set Y by an edge. So there will be no edge between the two, between the vertices of the same set. Now let us consider two groups, group 1 and group 2. So a bipartite graph in which the two vertices of the graph are divided into two sets here. So here the vertices are divided into two sets, that is group 1 and group 2, that is A to J, again B to G, again B to H, again C to F, again D to H, again D to I, and again E to I, and again E to F. So here this is an example for a bipartite graph. That's it. Yes, the group 1 and group 2. So that is the set X and Y such that every vertex of the set X, suppose if it is X and this is Y, so group 1, group 2 is considered as X and Y, then connected to the vertex of the, every vertex of the set X is connected to the every vertex of the set Y by an edge. There will not be any edge between the two vertices. So this is an example for a bipartite graph. So this is a bipartite graph. Now let us come to the next concept, the very important concept, that is isomorphism, isomorphic graph. This is very important and simple concept. If the number of edges and number of vertices are same, then the graph is said to be an isomorphic graph. That's all. If the number of edges and number of vertices are same, that is, let us consider two graphs G1 and G2. If G1 and G2 are the two graphs, these two graphs are said to be isomorphic if and only if the number of vertices is equal to number of edges. That is, the number of component vertices and edges are same. So the number of vertices is equal to number of edges, then the graph is said to be an isomorphic graphs. Their edges are connective. The connectivity is to be retained. There should be a continuity. Now let us consider a simple example for isomorphic graph. Now let us consider an example for isomorphic graph. Now let us consider there are 5 vertices V1, V2, V3, V4 and V5. Now, so the number of vertices here are, number of vertices are 5 vertices. Now let us draw the graph. So V1 to V3, again V3 to V5, again V5 to V2, again V2 to V3 and again V3 to V1. So there are 5 edges. So the number of edges are also equal to 5. So therefore, this is an example for an isomorphic graph. That is, the number of edges and number of vertices are same. So see here, let us consider this as E1, then E2, then E3, then this is E4 and E5. So 5 edges and 5 vertices are there. This is an example for an isomorphic graph. Now let us consider one more example. There are 5 vertices V1, V2, V3, V1 dash, V2 dash. So V1, V1 to V2, V2 to V3, V3 to V4, V4 to V5 and again V1. So number of vertices, number of vertices are 5 and the number of edges are also equal to 5. So 5 is equal to 5. Therefore, this is also an example for an isomorphic graph. So number of vertices and number of edges are same in this case. Hence, this is also an example for isomorphic graph. So in the examination, they may ask what is define isomorphic graph and give an example. Now that is, let us take one more example for isomorphism. So let us consider this graph G1, G2 and G3. So here the number of vertices are V1, V2, V3 and V4. Again this is V5, V6, V7 and V8. So the number of vertices, number of vertex is equal to 8. And let us check how many edges are here. So let us call this as E1, E2, E3 and E4. This is E5, E6, then E7 and E8. So the number of edges is also equal to 8. So the number of vertices are 8 and number of edges are also 8. Therefore, this is an isomorphic graph. This is an example for a isomorphism. Now let us consider this graph G2. Here the vertices are V1, V2, V3, V4, V5, V6, V7 and V8. Now let us draw here V1 to V2, again V1 to V4, again from V2 to V5, again V2 to V7, again from V3 to V5 and V6, again from this V3 to V8, again we have from V4 to V5 and V6. Check the number of vertices here. Number of vertices are 8 vertices and the number of edges, how many edges are here? So here the number of edges are 8 and number of vertices also 8. So therefore this is also an example for a isomorphic graph. So this is an example for isomorphism. Now let us come to the next property. Next graph G3. Here the number of let us start from this. Yeah, let us call it as A, B, C, D, E, F, G, H. How many vertices are there? The number of vertices 1, 2, 3, 4, 5, 6, 7, 8. Number of vertices are also 8 and the number of edges, let us represent this as E1, E2, E3, E4, E5, E6, E7 and E8. So the number of edges is also equal to 8. So number of vertices is equal to number of edges. Therefore, this is also an example for an isomorphic graph. That's it. Okay. Now, hope you got an idea regarding isomorphism. Now, let us come to the next one. The representation of a graph. Very important concept. The representation of a graph. So, a graph can be represented in many ways. The two most important and common way of representing a graph is adjacency matrix and adjacency list. So, a graph can be represented in many ways. The very important and the most common way of representing a graph is adjacency matrix and the adjacency list. This very important concept. So a graph can be represented by two methods, that is adjacency matrix, another one is the adjacency list. Now let us discuss regarding adjacency list first. Now adjacency list of a direct graph can be formed by listing all the vertices that are terminal vertices of a edges starting at the each vertex of the graph. That is adjacency list of a direct graph can be formed by listing all the vertices, just by listing all the vertices that are terminal vertices. So, listing all the vertices which are terminal vertices of edges starting at each vertex of the graph. Now, let me explain by taking a simple example. Let me explain by taking a small example. Let us consider a simple graph. Vertices V1, V2, V3 and V4 are the vertices. Okay. Now, just make a list vertices and here adjacency. Now, so how many vertices are here? V1, V2, V3 and V4. Now, let us write the adjacency for this. See, what is the definition? According to the definition, adjacency list of direct graph can be formed by listing all the vertices that are terminal vertices of the edges. See, here V1. So, V1 terminates at V2 and V4. So, therefore, the adjacency for V1 is V2 comma V4. So, the adjacency for V1 is V2 and V4. Adjacency for V2. So, V2 terminates at V1 and V3. So, V1 comma V3. Similarly, for V3, the adjacency for vertex V3 is V2 and V4. So, V2 comma V4. Similarly, for the last vertex V4, the adjacency is V3 and V1. So, V1 and V3. This is how we are going to write the adjacency for a given set of vertices. That's it. Okay. So, that is the terminal vertices of the edges will give the adjacency. That is, for V1 it is V2, V4 and V2. For V2 it is V3 and V1. For V3 it is V2 and V4. For V4 it is V1 and V3 are the adjacency for the given graph. That's it. Very simple concept. Right. Now, let us come to the next concept. Adjacency matrix. This is very important part. Adjacency matrix of a simple graph is denoted by A or AG. A or AG will represent the adjacency for a given graph of a graph G with respect to the number of vertices 1, 2, 3, 4, etc. n. So, the adjacency matrix is denoted as A or AG, and adjacency matrix is denoted by n cross n, n by n, n into n, 0 and 1 matrix with Aij is equal to 1 if I comma j is an edges of G, 0 if otherwise. The adjacency matrix is denoted as A or AG and is given by a n cross n matrix whose elements are 0 and 1. So, a adjacency matrix A or A is denoted as A ith row and jth column, where Aij, this is equal to 1 if I and j is an edge. If it is an edge, then that is equal to 1. Otherwise, we are going to consider it as 0. So, therefore, the elements in the adjacency matrix are 1 and 0. So, that is Ij is an edge of G, or whenever if it is I and j, then it is equal to 1. The edge is 1. Otherwise, it is a 0. Okay. Now, let us take an example. The adjacency matrix for the following graph. So, how many vertices are there? 1, 2, 3, 4 vertices are given. So, let us write the direction 1 to 2, 2 to 3, again 3 to 4 and 4 to 1. Okay, this is the direction. Now, here 4 vertices are there. The adjacency matrix AG or A is equal to, let us, this is a 4 rows 4 column matrix, 1, 2, 3, 4, again 1, 2, 3, 4. So, 4 rows and 4 column. Now, see, just according to the definition, adjacency matrix of a simple graph is nothing but the number of vertices 1, 2. If it is an edge, then it is 1, otherwise it is a 0. Now, here 1 to 1, 1 to 1 there is no an edge, 1 to 2 it is 1, again 1 to 4 there is 0, and again 1 to 4 there is 1 edge, 1, 0, 0. Similarly, if you come to 2, 2 to 1, 2 to 1, so the direction is different, it is 0, again 2 to 3, 1, again 2 to 2, 2 to 2 it is 0, 2 to 2 is also it is 0, again 2 to 3, 2 to 3 it is 1, again from 2 to 4, 2 to 4 it is 0. Again if we come to 3, 3 to 1, so 3 to 1, 3 to 1 there is no connectivity, 0, again 3 to 2 it is in opposite direction, 0, again 3 to 3, 3 to 3 is also 0, only 1, 3 to 4 is 1. Again from 4, 4 to 1. So 4 to 1 it is 1, and again 4 to 2 0, again 4 to 3, 4 to 3 it is 0, again 4 to 4 it is 0. So this is a 4 cross 4 adjacent matrix. That's it. Hope you followed. Now let us come to a next example. So in case of undirected graph, so if an undirected graph is represented like this, if there is no direction, then how to write the adjacency matrix for this? Now write down how many vertices are there: A, B, C, D and E. A, B, C, D and E. So it's a 5 vertices, 5 rows, 5 column matrix, adjacent matrix. A of G is denoted as A, B, C, D, A, B, C, D. Now here A to A 0. A to B it is 1, again A to B it is 1, again A to C there is no, yes there is 1, A to C is 1, again A to D is 1, A to D is 1, again from A to E it is 0. Similarly, if you come to the second row, B to A, so here B to A it is B to A 1, again B to 0, B to B it is 0, again B to C it is also 0, again B to D is there, B to D is 1, and again B to E, that's equal to 1. Similarly, if you come to C to A, so from C to A it is 1, C to A is 1, C to C is 0, again C to D is 1, and C to E is also equal to 0. If you come to the fourth row, that is D to A is 1, again D to B is also 1, and again D to C is also 1, again D to D it is 0, D to D there is one self loop, it is 1, and again D to E is also equal to 1. And the last one is, so here D to D a self loop, since this is a self loop, so here D to D is 1, right. Next E to A is 0, again E to B is 1, again E to C there is no, E to C is 0, again E to D, E and D is 1, and again E to E is equal to 0. So this is an example for a undirected graph whose adjacency matrix is, this is adjacency matrix for a undirected graph. Hope you followed. Okay. Now let us come to the next problem, directed graph. So we have to find the adjacency matrix for this directed graph. Now let us consider if the graph is not directed, it is not a directed graph. Now for undirected graph, so undirected graph, the adjacency matrix is AG is equal to, if I write the adjacency, this is just like a previous problem, this is the adjacency matrix for the previous problem. So if the directions are not given, then we can easily write A to A is 0, A to B is 1, A to C is D, A to D is 1, and A to E is 0. Similarly, B to A, suppose if it is undirected, then B to A is 1, B to B is 0, and B to D is 1, and B to E is 1, and the remaining cases are 0. C to A, so here C to A is 1, and again from C to D, so C to D is 1, remaining cases are 0. And if we come to D, if the direction is not given, then for all D to A, D to B, D to C, D to D, and D to D is also a self loop, so therefore we are going to get a graph adjacency matrix like this for a undirected. For a directed, so I will write here for this directed, write down the values A, B, C, D and E. Here A, B, C, D and E. So a matrix of order 5 rows and 5 columns. So directed graph, for directed graph, this is for a directed graph. So A to A it is 0, A to B is 1, Again A to C, A to C is 1. Again A to D is 0, A to E is also 0. Next from B, B to A. So B to A it is 0. Again from B to B, B to B is also 0. B to C, B to C is also 0. Again from B to D, B to D it is 1. Again from B to A it is 1. Similarly, if you come to C, C to D is 1, C to D is 1, and in other cases it is 0, that's it. And D to D is 1, D to D is 1, it's a self loop, D to D is 1. In other cases, we have D to E is also equal to 1, and D to A is also equal to 1. In other cases, it is 0 and 0. The last one, E to, again from we don't have anything, E to A is 0, E to B is also 0. Again from E to C is also 0. Again E to D is also 0, E to E is also 0. This is an adjacency matrix for the graph which is a directed, and this is for a undirected. If the directions are given, you are going to get the adjacency matrix like this. If the directions are not given, we are going to get a matrix like this. Hope you followed for a directed and a undirected graph. So this is how we are going to write the adjacency matrix for a direct and a undirected graph. Hope you followed regarding the adjacency matrix. So these are the basic things regarding adjacency matrix of a directed and a undirected graph. So that's all regarding today's session. Let us meet with the different concept in the next session. Thank you. Thank you very much.